In this lecture, we're going to go about trying to find the answer to a deceptively simple question. How long will the sun shine? Stars are big balls of gas that shine because they are hot. Stars are constantly losing internal energy, or internal heat, by shining. We call the amount of heat they lose per second the luminosity. Luminosity is a measurement of the rate of energy loss of a star. To stay hot, stars must somehow make up for the energy they're losing, otherwise they will eventually just cool and fade away. Sun's clearly been shining for a very long time, at least on geological timescales. And so one must look for what is the energy coming off the sun, that is its luminosity, a quantity we can measure, and then ask the question, how long can it maintain that luminosity? What source of energy does it tap in order to shine? This is where we now get to the question, how long can the sun continue to shine? To answer this question, we need to have answers to two fundamental questions. The first, what is the internal energy content of the sun? How much energy do we have to work with? How many joules per second can we squeeze out? And the second is how fast is this energy being lost to shining? We already know the answer to that. That's the luminosity. These two are related together to form the formula that the lifetime of the sun is the internal energy divided by the luminosity. In other words, how much energy have you got divided by how fast are you getting rid of it? You'll notice that this is very similar to a distance, time, speed kind of problem, in which one says, I want to go a certain distance, I've move at a certain rate, and I can compute how long it will take me to make the trip. Whenever we're dealing with a rate type of equation like this, it's relatively straightforward to notice that if you're computing the lifetime, the amount of stuff that you're expending is always on the top, and the rate at which you're expending it is on the bottom. In this case, the lifetime of the sun, or an estimate of the typical time scale of the sun to shine at a steady, more or less steady rate, will be how much energy you have divided by how fast, the rate at which you are losing that energy to luminosity. In the 19th century, there were two sources of energy that were known to scientists and were considered when trying to answer the question, how long will the sun shine? The first of these is chemical energy. This is burning through oxidation. Coal, wood, oil, etc. are all familiar to us every day. They burn by combining oxygen with basically a carbon-bearing compound of some sort. That oxidation reaction releases energy and produces carbon dioxide as a byproduct. Muscle power is an example of chemical energy. In this case, we're burning hydrocarbon fuel in our bodies and we're expending energy. We're able to do work with our muscles. And perhaps a more spectacular form of chemical energy is a chemical explosion, a very rapid exothermic reaction, one that produces an awful lot of heat very, very quickly. If it dumps too much heat, the heat dump can actually cause a supersonic blast wave to come off, and we call that an explosion. So we want the sun to be able to shine, but not explode. The other source of energy that was familiar to people in the 19th century and before is gravitational energy. A particular example of this would be water running downhill to power, like a water-powered water mill, like is shown here in the photograph. Another, perhaps less obvious example of gravitational energy is heat from a meteoritic impact. If a rock meteor hits the Earth, it's going to fall into the Earth's gravitational field and accelerate, and that acceleration is going to basically release heat energy upon impact. So you could imagine, and people in fact did all the way back to Newton, that you might be able to power the sun through gravitational energy. That perhaps what you had was a continuous rain of meteorites upon the sun, and the energy of impact could be sufficient, they thought, to possibly power the sun for some amount of time. Let's consider chemical energy as one possible way to power the sun and see where we get with this. The most powerful chemical reactions we know of will release an energy of about 10 to the 8 joules per kilogram of stuff being used as fuel. I'm going to define fuel very broadly as meaning stuff that is a source of energy of some form, usually in the form of a release of heat. The joule is the metric unit of energy. So, for example, if we wanted to power the sun through chemical energy of some kind, for example, we could imagine the sun being an enormous lump of coal and we're going to burn it. Let's ignore the fact that we don't exactly know how to get oxygen up to the sun to cause combustion, but let's say we're going to, a different way of looking at it is, we're going to power the sun by breaking chemical bonds. The most powerful ways we know of on Earth in which chemical bonds can break will give you an energy yield of a few hundred million joules per kilogram of fuel in the most powerful form. The sun's mass is measurable. We can measure it from the orbit of the Earth and the planets. It's about 2 times 10 to the 30 kilograms. So the total chemical energy that would be available to us if we had to use a chemical energy source of about 10 to the 8 joules per kilogram is found by multiplying the mass of the sun, 2 times 10 to the 30 kilograms, by the energy yield, in this case 10 to the 8 joules per kilogram, and we get a number of 2 times 10 to the 38 joules of total available chemical energy. That's a measure, an estimate, in order of magnitude of the sun's internal chemical energy content. What is the sun's luminosity? Again, a number we can measure. The sun's total luminosity is about 4 times 10 to the 26 joules per second. Those of you who've been paying attention to solar luminosity from earlier lectures will recognize I usually express this as 4 times 10 to the 26 watts. The unit of the watt is 1 joule per second. So we have 2 times 10 to the 38 joules of chemical energy available in the sun if we wanted to power the sun chemically. And we have to come up with an energy loss or deal with an energy loss of about 4 times 10 to the 26 joules per second. The lifetime is the energy content divided by the luminosity of the sun, which is 2 times 10 to the 38 joules divided by 4 times 10 to the 26 joules per second. We do the numbers. That turns out to be about 5 times 10 to the 11 seconds. There are roughly 3 times 10 to the 7 seconds per year. Do the calculation carefully. You find that the lifetime of the sun by chemical energy is approximately 16,000 years. Okay? So if we wanted to power the sun by chemistry, we could do so for only about 16,000 years. But even in the 19th century, geologists in the late 19th century had estimated that the Earth was anywhere from 100 million to 1 billion years old. So chemical energy is not going to do it for the sun. The chemical energy is insufficient to power the sun and have the Earth be a stable geologic place with life on it for 100 million to 1 billion years. This led to a fundamental problem, almost a paradox. How could the Earth be older than the sun? How could the Earth exist and have life on it long before the sun would have burned out? So this is a problem. We can call this the 19th century energy crisis. They knew the sun was producing power at a rate of about 4 times 10 to the 26 joules every second. Where are you going to get that kind of energy and get it for geological timescales? Well, chemical energy is not going to do it, but what about gravitational energy? Recall from a previous lecture, the interior structure of a star, and the sun is a star, is determined by the balance between gravity and pressure. Gravity keeps pressure from making the star fly apart by trying to make the star collapse in upon itself, make it contract and get smaller. Pressure, on the other hand, works in the opposite direction. It supports the star against gravitational collapse by trying to make the star fly apart. When gravity and pressure are in exact balance, we say that the star is in a state of hydrostatic equilibrium. When we think of equilibrium, we think of something sitting in a balance and sitting still, unchanging, not moving. Like if you brought a balance beam into exact balance, it would stop rocking back and forth. But not all equilibriums are just sitting still. Sometimes an equilibrium is just a starting point. And the question is whether that equilibrium is stationary, just sitting still, or whether it's a bit more dynamic. Let's take a closer look at what goes on inside of a star like the sun in a state of hydrostatic equilibrium. If we start out with the sun in a state of hydrostatic equilibrium, pressure is balancing gravity. I've shown at a particular place here inside this model sun, pressure trying to push out and gravity trying to push in. In this state of equilibrium, the sun neither contracts nor expands. But the sun's not sitting there, because the sun is radiating away energy. It's got a luminosity. Luminosity carries away about 4 times 10 to the 26 joules every second. If it's carrying away energy, it's bleeding off some of the internal heat of the sun. And we may recall that the pressure law, the law of a perfect gas, says the pressure is related to the density times the temperature. If you're bleeding off heat, you're changing the amount of internal energy, and the pressure is going to drop a little bit in response to this. So now we started out in a state of hydrostatic equilibrium, but because the sun is shining and radiating away a little bit of its energy, 4 times 10 to the 26 watts, it's going to tip the balance of the equilibrium ever so slightly in favor of gravity. So hydrostatic equilibrium in a star is not stationary because the star is losing energy. When it loses energy, it loses pressure, and something has to give. And what gives is the pressure drops ever so slightly, and gravity gets the upper hand. So now gravity is slightly stronger than the pressure. If gravity is slightly stronger than pressure, then the star, the sun, will begin to contract a little bit. It will shrink a little bit in size. Now, the sun is smaller, but it's also, remember, more tightly gravitationally bound. All of the bits of the sun are closer to the center. The gravitational force is stronger of every bit pulling on every other bit, and as a consequence, the gravitational binding energy of the sun has now increased a tiny bit. Now, I've drawn a dashed line here on this diagram to show where the surface of the sun was before, and then after the edge of the yellow line is where the sun is now. I'm exaggerating this a great deal just for effect. Don't think the sun would shrink that much that fast. But it does shrink, it does contract, and it becomes more tightly gravitationally bound. But the sun's not done. If it's more tightly gravitationally bound, that means that the sun is now compressing. But if the sun is compressing, that increases the internal pressure. And it increases the internal pressure to the point that it temporarily restores hydrostatic equilibrium, but now the restoration of equilibrium is in a slightly smaller sun with a slightly higher internal higher gravitational binding and pressure than before. So the state of hydrostatic equilibrium is not a stationary quantity, it's an instantaneous statement about the state of the gas inside of a self-gravitating star. If there is no other source of energy at play, when the star loses energy, it's going to shrink under gravity, get smaller, compress, and make up for that lost energy by tapping gravitational binding energy. In the case of this mechanism, what happens is you look at the amount of energy lost. The star will contract just enough so that the energy lost is exactly made up by the higher gravitational binding energy. This particular mechanism for generating energy through tapping gravitational binding energy in a slowly contracting star has a name. It's called the Kelvin-Helmholtz mechanism. The Kelvin-Helmholtz mechanism is a way to use gravitational binding energy to power the sun. The gravitational binding energy of the sun can be computed. E sub g is approximately g times the mass of the sun squared divided by the radius of the sun. At this instant, the gravitational binding energy of the sun is approximately 4 times 10 to the 41 joules of energy. Remember that the sun's luminosity, the rate at which it is losing energy, is 4 times 10 to the 26 joules per second. Using our lifetime formula, we can compute that the lifetime of the sun, being powered by gravitational contraction, should be the gravitational binding energy of the sun divided by its luminosity. If I plug in 4 times 10 to the 41 joules divided by 4 times 10 to the 26 joules per second, I get a lifetime of approximately 10 to the 15 seconds. The year is approximately 3 times 10 to the 7 seconds long, so 10 to the 15 seconds corresponds to approximately 30 million years. In the 1880s, when this calculation was first done by Kelvin and Helmholtz, geologists had estimated that the age of the Earth must be at least 2 billion years old. Once again, we find ourselves with an energy crisis. Neither chemical energy nor gravitational energy are sufficiently efficient. They don't yield enough energy per kilogram of star stuff to be able to explain why the sun should be shining for billions of years. And there's virtually no way around this. You cannot squeeze more energy out of gravitational contraction than through the slow leakage of the sun. If you tried to make the sun contract slower, you would not liberate enough gravitational binding energy to be able to make up for the energy losses of the sun. This is a problem. And it requires not some trick of chemical energy or a trick of gravitational contraction, but as we're going to see, it's going to require new physics.